Hi, I am Prasanna. I have implemented a decentralized exchange, also known as DEX, using Solidity for the Module 3 project. The motivation behind understanding how decentralized exchanges work was due to the recent collapse of FTX, a centralized cryptocurrency exchange. My implementation of the DEX is based on Uniswap's white paper. The main problem while building a DEX is maintaining liquidity. Liquidity is essential for making transactions possible. Uniswap solves this problem by allowing anyone to become a market maker and rewarding the liquidity providers proportional to their contribution to the liquidity pool. These type of exchanges are also known as automated market makers. These were some of the challenges I have tried to solve in implementing the DEX. Users can trade the listed tokens for ETH for tokens, or one token for another using the DEX. Now we will understand how does the DEX work. Uniswap is a constant product market maker, which means it is based on a constant product formula. Let X be the amount of currency A in the liquidity pool and let Y be the amount of currency B. Let K be a constant known as the exchange invariant. After every swap, X into Y should remain constant. We can plot the reserve of B versus the reserve of A, and we can see that it follows a hyperbolic path for a given exchange invariant. As the hyperbola never crosses the x and y axis, the reserves are infinite. This mechanism protects the pools from being drained. This also aligns with the law of supply and demand. The higher the amount you want to trade relative to the reserves, the less you get. Suppose a trader wants to trade delta x amount of A. Using this formula, we can calculate delta y, which is the amount of B that the trader will get in return for delta x amount of A. The price of A in terms of B and the price of B in terms of A can be calculated using this formula. Adding liquidity does not change the price as the ratio of reserves of A and B remains the same. It just increases the exchange invariant. The liquidity providers provide liquidity to the exchange by storing ETH and an equivalent amount of tokens in the liquidity pool. They need to be rewarded, which would encourage others to join the liquidity pool. The easiest way is to charge a small fee around 0.25% for each swap by the users and add it to the liquidity pool. For example, this ETH to token swap given X ETH returns the tokens corresponding to only 0.9975 times X ETH. The remaining ETH are added to the liquidity pool. This is the reason why the exchange invariant increases as the number of swaps increase. Providing liquidity is similar to owning a percentage share of the liquidity pool, which the liquidity provider can withdraw later. They are not entitled to withdraw their exact investment in terms of the absolute quantity of each token. Instead, a liquidity provider who owns or who provided X% currency A and B is authorized to remove X% of each reserve for those currencies, assuming their percentage was not diluted by other new providers. When new liquidity providers add liquidity, the exchange must update the percentage share of the old liquidity providers. Similarly, when an old liquidity provider decides to withdraw liquidity, the percentage share of the existing liquidity providers needs to be updated. A brute force way to do this is to maintain a mapping from the address of the liquidity providers to their percentage share. The problem with this approach is that the amount of gas required will grow linearly with the number of liquidity providers, and the exchange will only work on a small scale. The more elegant way to solve this is to provide LP tokens to the liquidity providers. which indicate their share percentage in the exchange. LP tokens are ERC tokens issued to liquidity providers in exchange for their liquidity. LP tokens represent the share of a liquidity provider in the liquidity pool. The fees are distributed proportionally to the amount of token one holds, and when LP tokens decide to withdraw from the liquidity pool, they get back their liquidity plus their share of the liquidity plus the accumulated fees. The LP tokens do not have a supply limit and new LP tokens are minted when new liquidity is added and when old liquidity providers decide to withdraw, their tokens are burned. This ensures that the number of LP tokens assigned to a liquidity provider indicate their correct share in the liquidity pool, irrespective of whether new liquidity is added or some old liquidity is withdrawn. The amount of LP tokens minted when a new liquidity provider joins the liquidity pool is given by this formula. We can understand this by an example. Let's say initially there was only one liquidity provider, LP0, who owned 100% of the shares, is equal to X. Now LP1 adds 2x ETH and 2y tokens to the liquidity pool, which maintains the ratio of the reserves. The number of shares or the number of LP tokens minted for this user is equal to total amount, which is X, multiplied by E deposited is 2x divided by X, which is 2x. So the shares of LP1 is equal to 2x, and we can see that the percentage share of LP0 is 33.33 or 1/3, as LP0 deposited X ETH and LP1 has deposited 2x ETH. So we can see that these shares indicate the percentage of liquidity. Using LP tokens, we can dynamically assign the percentage share to each liquidity provider without using much gas. Currently, there is a significant issue with our exchange as it does not account for slippage. Many users can try to trade tokens on our DEX simultaneously. There can be a difference in the exchange rate between the submission of a trade and the actual addition of that transaction on the blockchain. This shift in exchange rate is known as slippage. Attackers can make use of this to create sandwich attacks. Assume that at time t equals to 0, Alice submits a swap transaction to convert a large amount of A to B. Bob, who is an adversary, gets to know about this and he places a large buy order for B. If Bob's buy order of B gets approved before Alice's trade gets approved, she will receive less amount than expected of B. This is because Bob artificially inflated the price of B. Alice's trade will further increase the price of B, and Bob then sells B at the end for a large profit. Thus, we can see that sandwich attacks are bad for users, as users pay higher exchange rates than the true asset value. Sandwich attacks can be avoided by allowing users to set some maximum slippage while submitting the transaction. Now that we had a look at all the concepts, we can understand the code. I have used Hardhat, which is an excellent development environment for Ethereum software. It has a local Ethereum network node designed for development. It allows us to deploy contracts and run tests all within the confines of our local machine. The contract token is inherited from ERC20 token provided by OpenZeppelin. The contract exchange too is inherited from ERC20. This is the LP token provided to the liquidity providers. The token address has the address of the token that is traded on this exchange. A single token can be listed on one exchange. Shares has the mapping of the LP tokens owned by each liquidity provider. We'll have a look at the add liquidity function first. There are two cases in this. If there are no tokens in the liquidity pool of the exchange, then the user is the first liquidity provider and has the power or gets to set the initial exchange rate. We mint the liquidity provider tokens, and set the value in the mapping accordingly. If the liquidity pool is not empty, then we will add or update the reserves according to the exchange rate present already, and then using the formula discussed earlier, we'll mint new LP tokens, and which updates the share percentage for all the existing liquidity providers automatically, and then we'll update the mapping. The remove liquidity function removes the liquidity for the liquidity provider corresponding to amount number of LP tokens. We first need to check if the liquidity provider who is requesting to remove liquidity actually owns amount number of LP tokens that is stored in this mapping. Then we find the ETH amount and the token amount corresponding to the LP token amount specified by the liquidity provider. We burn those many number of LP tokens, and this updates the liquidity or the share percentage of the existing liquidity providers. Then we update our mapping and we return or we transfer the ETH and the tokens to the ETH and the exchange tokens to the liquidity provider who is requesting to remove liquidity. Now we'll look at different types of swaps allowed by the exchange. First we'll look at the ETH to the token swap. This is done using the formula discussed earlier. Before that, we check if we specify the maximum slippage allowed using mint tokens. So the user who is calling this function expects to receive at least these many tokens. The formula which was discussed earlier is implemented in this function. We first remove the fees from the input amount and then get the given the delta x, we calculate the delta y which has to be returned, and then transfer the required amount to the user. Now we look at the token to ETH swap. The sender specifies the tokens that they wish to exchange for ETH and the min ETH. Min ETH is used to avoid slippage, too much slippage, and check if the ETH bought, that is the ETH corresponding to the token sold, is greater than min ETH. We use the same function used earlier in ETH to token swap to get the amount of ETH bought corresponding to the token sold minus the exchange fee, and then we transfer this ETH bought to the sender. I have used the testing functionality present in Hardhat to test the functions defined in the contracts, the swap functions defined in the contracts, which we have seen earlier. So here the contracts are deployed on a local Ethereum network, and the tests are run on this network. We'll start by testing the ETH to token functionality, ETH to token swap functionality. So we'll first understand the scenario. So we have an exchange which has 0.25% exchange fee. The first liquidity provider comes and adds liquidity by sending 5 ETHs and 250 tokens. Now the second liquidity provider comes and sends 5 ETH and 1000 tokens. But as the exchange rate is already set by the first liquidity provider, only 250 tokens are used out of these 1000 and 750 are returned back to LP1. Now the liquidity pool has 10 ETHs and 500 tokens. The exchange invariant is 5000 and the shares are as given here. 5 LP tokens each are given to LP0 and LP1 as they have equal contribution in the liquidity pool. Now a trader comes and wants to swap ETH with tokens and sends 1 ETH. Now we have to find what is the amount delta Y of tokens that is returned to the user by the exchange. This is found using the formula which we had seen earlier, and delta X is the amount that is sent by this trader after deducting the exchange fee. So we get this value. This value should be these many number of tokens should be returned back to the trader. So we simulate this in our tests and we expect that the token balance of the trader will be equal to this much, and we'll check later if these tests pass. Then we'll also see that if the exchange had the liquidity pool now has 11 tokens, 11 ETHs, 11 ETH and 500 minus these many number of tokens. So one thing which we can see is as expected the exchange invariant increases from 5000 to 5000 around 5001. This increase is not significant, but it is an incentive, or this, while removing the liquidity, this will be divided proportionally among the liquidity providers. Now we remove the liquidity, so LP0 decides to withdraw from this liquidity pool, and we check if half of these many ethers and half of these many tokens are returned back to the liquidity provider who decide to quit. This is 5.5 minus the gas, so these many ethers are returned back to LP, or this is the increase in the ETH balance of LP0, and this is the increase in the in the token balance of LP0. In the same way, we test the token to ETH swap functionality. We have one trader who is trying to remove out trying to swap 2 tokens for some ETH, and this is the liquidity state of the liquidity pool, and we expect around these many or these many ETH to be returned back to the trader, but the number of or the ETH amount of ETH that is returned back is the expected amount minus the gas that is required, and we check if the decrease in the ETHs in the liquidity pool is equal to this expected amount. Now we'll look at how token to token swap is implemented. We had seen earlier that one exchange lists only one token for trading. So we create a new contract factory that has a mapping from the exchange to the token that is traded on that exchange. We'll understand how token to token swap works using an example. Here trader wants to swap 10 token 1s for token 2s that are traded on exchange 1 and exchange 2 respectively. These are the states of the liquidity pools. We use the existing token to ETH and ETH to token swaps to achieve a token to token swap. First, the exchange 1 swaps the 10 token 1s for ETH and sends the delta y1 ETH to exchange 2 instead of sending it to trader. In exchange 2, delta y1 ETH is swapped with token 2 and the resulting delta y2 amount of token 2 is sent back to the trader. This scenario is modeled in the third test. Now we'll check if the test pass. So we run this command and we check if all the three scenarios which we had discussed earlier give the expected results. This is tested on my local machine on the local Ethernet network provided by Hard Hat, and we can see that all the three tests have passed.